Let's move on to the fourth video of this section, making error bars. In the previous section we saw how to create Gantt charts using Python. In this video we're going to display the dispersion of data on a plot. We'll first use some sample data that consists of 4 sets of observations, and then we'll step ahead to compute the mean value and 95% confidence interval for those observations. At the end we'll render bars with vertical symmetrical error bars. So let's now move on and see how to go about it. Error bars are useful to display the dispersion of data on a plot. They're relatively simple as a form of visualization. However, they're also a bit problematic because what is shown as an error varies across different sciences and publications. This does not lessen the usefulness of error bars, it just imposes the need to always be careful and explicitly state the nature of the error, visualized as an error bar. Let's now get ready to plot error bars. So, to be able to plot an error bar in the raw observed data, we need to compute the mean and the error we want to display. The error we compute represents the 95% confidence interval that the mean we get from our observation is stable, which means our observations are good estimates of the whole population. Matplotlib supports these types of plots via the matplotlib.pyplot.errorbar function. It offers several kinds of error bars. They can be vertical or horizontal and symmetrical or asymmetrical. Here in this code we've used some sample data that consists of 4 sets of observations, as you can see these arrays. And for each set of observations we compute the mean value. After this, for each set of observations we go on to compute the 95% confidence interval. And next we render bars with vertical symmetrical error bars. So this code will render a plot with error bars that display 95% confidence intervals as whiskers extended along the y-axis. Remember, the wider the whiskers, the lesser are the probability that the observed mean is true. Let's now dive into the working of this code. In order to avoid iterating over each set of observations, we use NumPy's vectorized methods to compute means and standard errors, which we use for plotting and computing error values. Using NumPy's vectorized implementations, which are written in the C language and called from Python, allows us to speed up computations by several magnitudes. This isn't very important for a few data points, but for millions of data points it can either make or break our efforts to create responsive applications. As you may note that we explicitly specified dtype equals np.float64 in the np.mean function call. According to the official NumPy documentation reference, np.mean can be inaccurate if used in a single precision. It's better to compute it with np.float32, or if the performance is not an issue, use np.float64. So we're now ready to run this code and see the output. As you run this file, you get the graph as the output. This is an ongoing issue with what to show on error bars. Some advise on using SD, 2SD, SC or 95% CI. We must understand what the difference between all these values and what they're used for in order to be able to give reasoning on what to use them and when. Standard deviation informs us about the distribution of individual data points around the mean value. If we assume normal distribution, then we know that 62.8% of data values will fall between plus or minus SD, and 95.4% of the values will be between plus or minus twice SD. Standard error is calculated as SD divided by the square root of n, where n is the number of data points. Standard error informs us about variability of mean values, if we're able to perform the same sampling more than once. The confidence interval is calculated from SE, similar to how the range of values is calculated from standard deviation. To calculate 95% confidence interval, we must add or subtract 1.96 times the standard error to or from our mean value, or use proper notation. The wider the confidence interval, the less we would be sure that we're right. You can see that in order for us to be sure our estimation is correct and that we are giving its proof to our reader, we should display the confidence interval, which in turn carries the standard error. This, if small, proves that our means are stable. Superb! In this video we saw how to display the dispersion of data on a plot with the use of error bars. In the next video we'll see how to make use of text and font properties.